Welcome to the Arctic Climate Modeling Program Mentor Lecture. We are very fortunate today to have Dr. John Walsh with us. He is President's Professor of Global Change at University of Alaska Fairbanks. He is Director of the Center for Global Change at University of Alaska. His research interests include climate of the Arctic, extreme weather events as they relate to climate, and the variability of snow and ice. He was lead author of the Arctic Climate Impact Assessment, and he is lead author for the Polar Regions chapter of the Intergovernmental Panel on Climate Change's most recent assessment. He is co-author of a textbook titled Severe and Hazardous Weather, which he has used in the classroom. So thank you very much for joining us, John.
Thanks, Barb. And thanks to everyone for tuning in. Again, we're sorry for the little delay, but I think we can make up for it in time. This topic is a very timely one, so we really welcome your perspective too. It's timely because climate's been in the news a lot, and Alaska is actually one of the focal points. It's one of the areas people are looking at when it comes to climate change. So I think we have a lot to offer the rest of the world here in terms of our insights and our experiences about what's going on. What I thought I would do today is step through a few basic questions with the emphasis on Western Alaska, your area. So you may see some diagrams and some maps here that are pretty close to home. And then we'll try to place your area into the bigger picture a little bit. But in terms of the material, I have a number of slides here. We'll try to take about half an hour, and then we'll get into the question and answer session after we finish with the slides. And I'll start with this introductory one, which lists the three questions we'll be looking at. First, we'll say a few words about what climate is. I think you all have a general idea, but we'll put down what it officially is, why it's important. Again, I think you have some ideas yourselves, but we'll look at why others are interested in climate from the viewpoint of its importance. And then we'll look at this question about whether climate is changing. And that's when things get interesting. And that's what a lot of the news has been about lately. On this first slide, I've put a few little pictures that are a tip-off to why climate is important. You see a polar bear and a seal. They're both very dependent on climate and climate change for their environment and their survivability, in fact. And down on the left there is a photo showing the wave action during coastal storms that seem to be increasing, especially in your part of the coast. So we'll start with this simple definition that climate is an average of the weather. And by average, they mean that some areas are warmer than others, some are drier than others, some have more storms than others. So we've summarized here the characteristics of the climate of Western Alaska. This is what most people learn when they study climatology and they come to Western Alaska. The winters are cold and wet wet usually means snowy because it's cold enough for snow instead of rain, and you have a lot of wind in your communities. Summers are mild meaning not hot and not cold. A lot of people would like that summer climate when they're living in cities that get hot in the lower 48 and in a lot of the rest of the world. The ice and the snow usually retreat, go away around this time of year, April and May. And then we have the most storms during autumn and winter in Western Alaska. That's not the same as the climate in much of the rest of the world, but it does capture the basic features of climate in Western Alaska. And here are some examples of temperatures, just to show you how the climate varies in an area like Western Alaska. In some ways, we're oversimplifying when we treat Western Alaska as one region. I've put down here the average high temperatures for the day in January. So your average January day would get this warm at some point. Barrow, which is not really Western Alaska, has a high of -13. It's as warm as it gets on an average day in January in Barrow. As we work our way south, Kotzebue 4 degrees, Nome 14, Dillingham 22, Adak 33. Adak's way out there in the Aleutians. But you can see how there's a range of 40 or 50 degrees in the average day in January, depending on where you are along the Alaskan coast. That's a pretty impressive range of temperature for one state, but that's how climate works. Now, let's turn to a few pictures here. This shows you the average snow and ice cover. By ice, we're referring to sea ice, and by snow, we're referring to the snow that's on land. This is the average snow and ice cover at about this time of year. You can sort of place yourselves in that picture. The pink and purple there represents ice cover. That's the ice out on the ocean, and we gave it that artificial color just to distinguish it from the land. Otherwise, everything would look white from a satellite picture. And you can see where the average position of the ice edge at about this time of year is north of the Aleutians, but it's definitely south of the Bering Strait. So villages like Nome, Kotzebue are normally iced in at this time of year, at least early April. And the white on land indicates that there's snow cover over almost the entire state, except when you get out onto that Aleutian Peninsula. Now, that's the average picture for April. If we turn to September, this is an average picture of the ice cover looking down, straight down from the North Pole here, so we've changed our viewpoint a little bit. It's the average picture of the ice cover in September, and this is going to lead us into climate change. You'll notice that the ice is farther north in September. That's part of the normal seasonal cycle of climate. It's warmer in the summer, so the ice melts back. But the ice, at least back around 1980, is still up pretty close to the coast of Alaska on the north end. It's going from Barrow over into the Chukchi Sea and then up against the coast in Siberia. What we're going to look at next is how that has changed as a result of climate change. So that's your picture in 1980. Now we're going to look 25 years later, 2005. And I'll step back and forth so you can see the difference here. It's 1980, 2005. Here's 1980, 2005. Notice how the ice has come way to the north, just into this Chukchi Sea area, north of the Bering Strait. This is the area of the most rapid loss of sea ice, and it's happened in just 25 years. It's roughly one generation of human lifetimes. And this is what's getting people's attention, the fact that the ice is changing so much, which is a sort of an indication here that climate is doing something over the last few decades. That picture there is 2005's September. That's during the summer, the late summer. Here's last summer, which is pretty much the same. Notice how the ice is way north of the Bering Strait, and there's plenty of room for ships to sail around the coastal areas there. And there's also plenty of room on the open ocean there for waves to build up when storms come along. And that has some implications for the coastal villages. And we'll come back to that one. So we're seeing that the ice cover on the ocean is actually retreating. It's going up to the north, leaving a lot more open ocean in western and northern Alaska. Now, here is a graph, the type that scientists look at to summarize what's going on in terms of numbers. It's a graph where on one scale here is the year, going back to about 1980 and coming up to last year. And they've graphed the amount of ice cover in September in the Arctic Ocean. And there's one curve there that shows the area that's north of the ice edge. The other, the lower one, is the amount of ice that's thick enough to walk on, essentially. But what you notice is this downward trend. The amount of ice has gotten smaller, and in the last few years, they've actually set record lows for the amount of ice that's been out there. In other words, we've had less ice at the end of summer in the last few years than at any time previously in the past 20 or 30 or even 40 years. So what's happening lately is unusual in terms of the history of ice. And here is a set of maps showing what computer models predict for the future. You'll notice over there on the left are some years. 1980 to 2000 means that period has already happened. But here's 2010 to 2030 in the second row, 2040 to 2060 in the third row, and then 2070 to 2090. So if you're, say, 12 to 15 years old now, and you're around for another 60 years or so, you'll probably experience this third row and maybe even the fourth row, the row down on the bottom. They've shown here what the computers predict, the computer models predict for ice cover. September, you'll notice that ice goes farther and farther north of the coast. It's barely in the picture there by 2070 to 2090. In the wintertime, there's still ice, actually, along the west coast of Alaska. That ice manages to come back, but it's very thin ice and unstable ice. And here's the type of ice that will probably be out there. This picture was taken just offshore of Alaska, and it's a sign of what a degrading ice cover means when you're trying to get around on the ice. These poor dogs are trying to figure out what to do because the ice is thawing, and it's thawing earlier than they had expected there. So when there's unstable ice, there are going to be problems, even though technically there is ice cover out there. It's thin and unstable. Now, what does this loss of ice mean? Well, it's not good for several types of marine mammals and animals. Polar bears are one of them. Polar bears have been in the news a lot lately. They require ice cover, especially during the reproduction cycle. And they also use ice cover as a platform when they're looking for food. And here's in this particular picture, we have, it looks like a mother and two of her cubs. This retreat of the sea ice is now such a concern that the United States Fish and Wildlife Service is proposing that polar bears be considered an endangered species. They're actually worried that polar bears may not survive for another 50 or 100 years if this ice cover keeps retreating. In the summer, they'd have to swim hundreds of miles to get to ice cover if that computer model prediction that we just saw is right. So polar bears clearly have a stake in what's happening with the ice cover. Here's a picture of where the polar bears are already being affected by the ice cover. You might recognize that area. That's Hudson Bay. Over here on the west side, there are a lot of polar bears. At least there used to be a lot of them. That ice cover in Hudson Bay has been going farther and farther from shore. And what the biologists are discovering is that polar bears are getting thinner and thinner because the ice cover is so far away that their eating habits are disrupted, their feeding habits are disrupted. And that was the area that really caught scientists' eyes, the biologists' eyes first, for one where the polar bears are threatened. Now they're realizing that this type of problem could exist even in Alaska and along the Russian coast. So the polar bears in this area are already having trouble. Another type of marine mammal that people are worried about are seals. A lot of seals depend on the ice cover for their habitat and for their dens when they have young pups. Here's a seal here who's come up in water that doesn't have much ice on it. If you look closely, there are a couple of little chunks. There's not enough to land on or to sit on and rest on. So there's a lot of concern about whether seals will be able to survive far into the future as the ice cover retreats. Now we'll look at a couple other examples of changes in the ice and snow, and then we'll turn to climate itself for a few minutes, the things that are making the ice and snow change. Here's a picture of a glacier. It's McCall Glacier. It's up in the Brooks Range. These two pictures were taken about 45 years apart, 1958 on the left and 2003 on the right. So that right one is just a few years ago. If you look closely, you notice how that glacier has retreated. It's farther up into the valley. There was ice down south of that little, or just below that little ravine in 1958. Now you can see that whole wall, the canyon where the glacier used to be. This is very typical of what's happening to Alaskan glaciers. Because our climate is warming, the glaciers are melting more and retreating. That's true also of the glaciers down in southeastern Alaska. And then we have Greenland. It's the biggest ice sheet in the northern hemisphere. Here's a chart showing how much of Greenland was melting in 2 different years. 1992, it's only 15 years ago. The red area is the part of Greenland that melted during the summer of 1992. So this is probably about the time some of you were born. That's the amount of Greenland melt, that red area. Just 10 years later, look at the amount of red on Greenland. It's almost half of the ice sheet that melted during the summer. So we've got Greenland feeling the effect of this climate warming that's going on. More and more melt, and the change has happened just in the last 10 or 15 years. So we're seeing these changes in the Atlantic side of the Arctic as well as on the Alaskan side. Here's what the consequence of that melt on Greenland is. This is a picture that somebody took on the Greenland ice sheet in the summertime when that melt was going on. Here's this big canyon. That blue stuff is water. It's the meltwater where the snow is melting and falling into a crevasse. And that water eventually makes it out into the ocean. There's a lot of concern that that extra melt may raise sea level, may make sea level higher around the world, because there's a lot of water stored up in the ice on Greenland. If that ice melts, we have sort of a contribution to the height of the ocean, or to sea level. So let's turn now to what's really making all this happen. Turns out that temperature is the main factor that's causing this loss of ice and snow cover, the melt of the Greenland ice sheet, and various other things. Here's a graph of the world's temperature going back 120 years or so. This is for the whole world, and the black line on there shows you each year's value. It's a dashed black line. The red is what they call a 5-year average, so it sort of smooths things out a little bit to show you the picture better. Over on the right are the last few years. Notice how it's gotten warmer. There's a scale there that's in degrees Celsius, so you have to double those numbers to see how much the warming is in Fahrenheit. It turns out that just over this last 120 years, the world as a whole has warmed by about 1.5 degrees Fahrenheit, about 0.8 degrees C. And the last few years have been the warmest on record. So it's probably not a coincidence that we've had the warmest years on record in the last few years, and also the greatest retreat of the ice cover near Alaska in the last few years. Now, I only have one table. The table's going to be tough to look at, but these have some interesting numbers on, and you may be able to see the ones that apply to very close to where you are. These are the amount of warmings at Alaskan stations over the last 50 years or so. There's a column there for different seasons. There's this one called annual, is the average warming for the whole year. Then there's a column for spring, for summer, for autumn, and for winter. And these numbers, the amount of warming at the various cities or villages in the last 55 years, going back to 1949. And the reason we put this into a table is that these are some of the largest warmings anywhere in the world. If you look at these numbers on the right for the West Coast, Bethel has warmed by, let's see, about 6 degrees Fahrenheit. King Salmon has warmed by about 8 degrees in the wintertime. In the interior, Fairbanks, to Big Delta, Bettles have warmed by about 8 degrees. Going down south, Anchorage is warmed by about 7 degrees. So the winters are now 6, 7, or 8 degrees warmer than they were back in 1949 or 1950. So 1949 or 1950 may be when your grandparents were born. So if your grandparents tell you it used to be colder back in their day, they're right, according to the actual temperatures. It's warmer by anywhere from, say, 6 to 8 degrees in the winter. If you look at the other seasons, it's warmed also. The redder the box is, the bigger the number is. But even in the spring and the summer, the warming is several degrees. Not as much as in winter, but it's still a few degrees of warming. And these amounts of warming in Alaska are higher than essentially any place else in the world. So if you're living in one of these areas that's warmed by 5, 6, 7 degrees in the winter, you could figure you're where people are looking for a preview of the future. Now, what's responsible for this? Here's the one physics diagram we'll look at. What most scientists think is responsible for the warming is the greenhouse effect. You might have heard about this. The greenhouse effect occurs when the sun heats the earth. They show you some lines here that represent the sun's rays coming in and heating up the earth. When the earth heats up, it gives off that energy in an upward direction. That's those squiggly arrows. Those are that's the Earth's energy trying to escape back to space so that the Earth doesn't overheat. It turns out that there are some molecules in the atmosphere that trap the heat. Look at that arrow there. It was trying to escape to space, but it got caught and sent back down to the ground. So it's giving an extra dose of warming to the ground. That's what's called the greenhouse effect. And it's caused by gases like carbon dioxide and methane and nitrous oxide. Those are the greenhouse gases. And the more of those there are, the more of this trapping of heat there is. And the more extra energy comes back down to heat up the ground. That's what they mean by the greenhouse effect. It's sort of the way a greenhouse works. A greenhouse traps heat with its roof. But in this case, the atmosphere is trapping heat with its molecules, its air molecules of a certain type, carbon dioxide and methane and those molecules. And here's the problem. If you look at the record of carbon dioxide in the atmosphere, they actually measure carbon dioxide at several places around the world. One of them's in Hawaii, where the air is not too polluted, so they don't have to worry about smokestacks right upstream. They also measure carbon dioxide at Barrow, and the graph looks almost identical to this. Here's 1960. Carbon dioxide had about 320 on the scale. 320 is parts per million of the molecule, so that's about 0.3% of the air molecules were carbon dioxide. The important point here is the trend. Look how that's gone up in the last 50 years or so. Gone from 320 to 380. That's about a 20 or 25% increase in carbon dioxide if you do the math on that. That's a significant increase of a greenhouse gas. If you look at the graph for methane, very similar. So what we're doing is increasing these greenhouse gases in the atmosphere. The amount of the heat trapping potential in the atmosphere is going up. So it's not surprising at all that the world is getting warmer, and we can attribute a large part of the warming in Alaska to this increase of the greenhouse gases. And if you remember that last graph and look at the temperatures that we looked at a while ago, this is the same temperature diagram, you'll notice they're very similar. There's carbon dioxide, and there's temperature. Temperature has a few more wiggles on it, as the winds can make the temperatures a little different from year to year, but if you compare those two, the trends are pretty similar. So when scientists say that they're looking for reasons why we're warming, this match between the carbon dioxide and the temperature patterns is what they call one of the smoking guns. It's the piece of evidence that they have to say the greenhouse effect is working. Now, let's look at a little animation here. This animation is going to show you what computer models are predicting for the next 100 years or so. In fact, we're going to look at Arctic temperatures from computer models in a map that's going to animate. I'll give you a short little movie. It's going to start in 1980. That's 25 years ago. But it's actually going to go to 2100. It's going to use the temperatures of the last 20 years as a starting point. We know those, but then it's going to make a prediction through 2100, which will be, let's say, 95 years into the future. Full screen. Now what we're going to do here is watch the temperatures, If you look at this diagram, there's a little calendar up there, which is the month and the year. You notice that 11/1980. That's where it's going to start, 1980. The scale on the right shows you whether it's cooler than average or warmer than average compared to our present day average. So green means cooler than average, yellow and red means warmer than average. In fact, as you go from yellow to orange to red, it's getting warmer and warmer compared to our present average. By the time you get to orange, it's 5 degrees Celsius warmer. That's about 9 degrees Fahrenheit warmer. So this particular month, November 1980, was actually cooler than the present day average by about 1 degree. So as we start this moving, you'll see that calendar advance, and it's going to go year by year until the year 2100. So I'll start it moving, and then we'll make the picture a little bigger too, so you can see it better. Hit start, and then we'll look at the full screen. So there it goes. Now you'll see we're just past 2005. There are sort of warm and cold areas. Maybe we can slow it down a little bit so you can see that clock better. We're up to 2030, but now notice how all the colors are yellow and orange. We lost the cool greens. We're now into the warm yellows and oranges, and we're getting to the hotter oranges and reds. We're up to 2060 here. Notice how each year is a little different, but they're all warmer than average. As we get to 2070 or 2080, we get into the hot colors over Alaska. Lots of oranges and reds, which means we're a lot warmer than we are now, maybe 8 or 10 degrees Fahrenheit. I think we'll go through it one last time here. Just went back to 1980. Notice how there are cool years and warm years, but nothing unusual through the 1990s. Now we're coming up to today. Things are pretty average. Mix of greens and yellows. Now we're up to 2010, and the yellows are starting to take over. 2020, almost all yellows. Just a few old green pockets left. 2030, the oranges are appearing. Oranges are warmings of 4 degrees, 5 degrees C. Then we get into these reds, occasionally and more frequently as we go to, say, 2060. We're now up to 2065. So 2 generations down the road, when you're grandparents, when you are grandparents, that's what the computers are saying the world will look like. It'll be warmer than at present by 5 or 6 degrees C, maybe 10 degrees Fahrenheit. So that's why the scientists are concerned about the trend we're seeing. The trend we're seeing is pretty consistent with that particular sequence that the computer models produce. So we're already seeing the beginnings of that trend the computer models are predicting. Now, what we'll finish up with are a few other ways that Alaska might be affected by warming. And this is what was just in that climate report that came out last week. These are some of the things they mentioned about Alaska, things that may happen as the climate warms. First thing is drier conditions in the summer. The reason there'd be drier conditions is that we would have more evaporation. When it's hotter, more water evaporates from the ground and from the lakes. Here's a picture of some lakes. These are actually lakes out on the Seward Peninsula, and this picture was taken from a helicopter. You can see a couple of lakes and a couple of former lakes here. If you look at that lake down towards the bottom, notice how you can see the old boundary of the lake, where trees haven't grown yet. There's just new grass, basically. That lake has been drying, and the shoreline has dropped. To the right of it is a lake that's essentially all gone. There's a little puddle left in the middle. That lake has dried. And if you look around, there are other signs of dried up lakes. The thinking is that there's been more evaporation lately, and there may also be thawing permafrost underneath these lakes, which is helping to drain them. The main point here is that lakes are drying. Here's one other set of pictures. These were taken by airplanes, showing different lakes in 1950, 1981, and 2000. In all cases, the lakes have gotten smaller. They've been drying up, literally, over the last 50 years or so. So this prediction of a drier Arctic is already showing up. Now, if it's drier in the summer, another thing we need to worry about, especially in the forest areas, are fires. And in interior Alaska, we've had some very bad fire years in the last 3 years. This picture here shows you a raging fire, and it makes the point that fires are a danger not just for people, but for wildlife. There are some deer trying to figure out what to do to get away from that fire. The best they can do is go down to this stream and hope that somehow the fire misses them. But that's not a good situation to be in if you're a deer. Here's a picture of fires from 2004. Now, I know your villages didn't have fires in the immediate villages, but most of interior Alaska did have fires, and you're under the smoke here in this picture. That pictures of Alaska. The Brooks Range is up there at the northern edge of the smoke. This is a satellite picture. The Alaska Range is down here in the south, and here's the west coast. So Nome is, I guess, Nome is out there, and the other villages that you're probably calling from are on the west coast. But look at how that smoke had actually reached way out into the Bering Sea. So if you were in your villages in that summer, you should have had some smoky periods when the smoke from these fires in the interior spread out to the west coast. The dots there, the red dots, show you where all the fires were actively burning. And this picture here on the right is a picture from right where we are here in Fairbanks, looking down towards our new museum, which is at the green dot. It's only a quarter-mile away. The smoke was so thick that we couldn't even see the museum a quarter-mile away on many of those smoky days. So this is something we have to be concerned about as the climate becomes drier. Second other way that climate might be affected and might affect Alaska is something that might be good, positive here, a longer growing season. Look at one graph of it. One of our forestry experts has been keeping track of how long the growing season is in interior Alaska, in Fairbanks. And he's got records going back to about 1900, when the growing season, which is the number of days between the last freeze in the fall, the last fall frost and the last spring frost and the first autumn frost, the length of time between freezing events was 80 days back around 1900 and 1910. It's now up to about 120 days, which means if you're trying to grow vegetables or if you're a tree that's trying to grow, you have 3 months instead of 2 months for growing. Many people would consider that a benefit of global warming, but it's actually showing up here in Alaska fairly dramatically. And the last item, which I know is one that does affect your communities, coastal flooding and erosion. A couple of factors at work here. One of them is that retreat of sea ice, and we put in parentheses the wave action here. The farther the ice is offshore, the more the winds from storms are able to build up waves. And here's a photo, I believe this one's Shishmaref. Ken can correct me if I'm wrong, but I believe that is Shishmaref during one of these coastal storms when the ice was far offshore and the coast actually eroded. Several feet of the landscape were literally lost during this particular storm. And to a large extent, the problem is this retreat of sea ice, but there's also another factor that's entering in. This is a picture of Nome after an October storm. There's a storm a couple years ago where downtown Nome flooded for the first time in recent memory, and that's the aftermath. The water had gone back down, but you can see that the water did some damage in downtown Nome. That other factor I mentioned are that there seems to be an increase in these storms. This is a satellite picture showing a storm off of northern Alaska There's Barrow, the Bering Strait is down here, so the northwest coast is right where the green arrow is. There seems to be an increase in the number of strong storms up in the Arctic Ocean. And one of our scientists, David Atkinson, has drawn up a graph showing the number of storms each year that has affected Barrow, which is on the north coast of Alaska. And his analysis goes back to about 1950. You can see that in the last couple decades there have been more storms, maybe 20 or 25 a year, compared to the earlier decades. I think his color code here is that black means a storm when there was lots of open water for waves to build up. The green means there was an ice cover off of Barrow. So the biggest increase in storms has come at a time when there's been open water offshore. So there seems to be this second part of the problem here, the increase of storms. But on top of that, there's all that extra open water that lets waves build up higher than they would have if an ice cover were present. So here's the last slide. It accepts the fact that global warming is happening. The Alaskan data and the experiences of Alaskans confirm that warming is going on in Alaska, and as we saw, the global temperatures show a warming. The warming for the rest of the world is not as much as in Alaska, but it's happening. And there are already impacts. More storms, growing seasons getting longer, less ice, the glaciers are retreating. So we have here two options, basically, or two possibilities for how to handle it or respond. We could certainly prepare for it. We can acknowledge that climate is changing, and it's probably going to continue to change to some extent. And if it does, we know that there will be probably more storms. We know it will be warmer, and we'll have these drier summers. The other is we can try to reduce it. We can try to reduce climate change. There are a couple of approaches there. The first one is at the individual level, or the sort of the small community level. We can use less energy, and the energy that we use, we want to use less of, is the energy that releases those greenhouse gases. That's the energy that comes from coal, oil, natural gas, and burning of wood. The more we conserve on those gases and energy, the less greenhouse gases we ourselves put into the air. But in the bigger picture, there's the rest of the world out there, which is contributing most of the greenhouse gas buildup. We can urge lawmakers to address climate change. Just in the last few years, I think the lawmakers, the senators and the representatives and the other legislators are starting to get the message that people are concerned about climate change. The response is not as fast in the United States as it is in some other countries, but as long as we keep getting the message through, I think we will see some action at the higher levels of government, which could have impacts on the rest of the country and its broader inputs of greenhouse gases. So that is the last one. I'll stop there and we can shift to the questions.
From all the forest fires in Alaska, is there a possibility that there is bald spots of trees in Alaska?
Is it a possibility that there are bald spots? I mean, places where trees will not come back?
Yeah. I mean, yes.
Yeah, there are. They call these things fire scars. If you fly over in an airplane, you might see an area that's several miles on a side that looks black, and that's where the fires were recently. Now there is a cycle of regrowth. First the grasses come back, then the shrubs, and then the small trees like the birches and aspen. And over a period of 100 years or so, those trees will reestablish themselves, but it takes a long time. I mean, it takes maybe 50 to 100 years to get back to where you would say there's a forest there. Now, what's interesting about the fire problem is that in the absence of people, one of the ways forests go through their natural cycle is to burn every several hundred years. Lightning starts fires, the forests burn and they regrow, so they get rejuvenated. So there is a natural cycle. The problem we're running into is that if the summers become much drier, we may be stepping up the pace of this cycle. It may be happening faster than in the past. And we're not quite sure what that's going to mean for the bigger ecosystems of at least of interior Alaska. But over the period of 100 years or so, you would see this bald area form and then gradually reacquire its old characteristics, but it would take a long time.
If the polar ice cap melts, how much water would rise? I mean, what parts of the world would be underwater?
The reason it's a good question is that there's an important distinction in the types of ice. If the water on the ocean melts, if the sea ice melts, it turns out that doesn't change sea level at all, because that water is already in the ocean, even though it was frozen as sea ice. But if we get to the glaciers and to Greenland and Antarctica, then we have major amounts of ice that get added to the ocean. The calculations for Greenland say that if the entire Greenland ice sheet melted, sea level would rise by about 20 feet, 7 meters. Now, 20 feet is the height of a two-story building. So if you imagine sea level getting higher by the height of a two-story building, there will be a lot of areas along the coast underwater. It turns out that a large part of South Florida, the Everglades, for example, will be completely underwater. In fact, Florida will lose hundreds of square miles of its area. Quite a few of the West Coast villages in Alaska would be affected by a 20-foot sea level rise. Now that's a worst-case scenario, losing all of Greenland. The Antarctic ice sheet is even worse, though. So maybe, I guess Greenland is the second worst-case scenario. The worst-case scenario is Antarctica, which would raise sea level by another 60 or 70 feet, which is the height of about an 8-story building. Now, the best estimates from scientists are that Greenland and Antarctica they're actually starting to melt, but it will be hundreds or thousands of years until they're completely gone. And we aren't even sure that greenhouse warming would continue for that long. So I think what we're going to see are slower rises of sea level, but just for perspective, you might keep in mind that a place like Greenland has enough water stored in its ice that it could raise sea level by 20 feet if it were to completely melt.
Would it affect the current in the ocean if the ice melts?
Yes, it would. That's something we didn't get into here. But it turns out that when ice melts, that's very fresh water. It doesn't have any salt in it. And that makes a difference for the ocean currents. Did any of you see that movie called The Day After Tomorrow? That was a movie where they made up some possibilities for what would happen if ocean currents were affected by melting ice. And what happens is a lot of the currents would stop because this fresh water from the melt would act like a lid on top of the ocean. It would actually prevent the currents from happening. And that would change the Gulf Stream. It would change the Kuroshio current that comes up from Japan and keeps the Aleutian area warmer than it would otherwise be. So there could be some consequences for the ocean currents of melting ice caps.
How would we reduce the ice from melting?
How would we reduce global warming?
How would we reduce? Well, they sort of go together. If we can reduce global warming, we'll reduce the rate that the ice is melting. The problem is that even if suppose that today we stopped putting extra carbon dioxide into the air, suppose carbon dioxide and these greenhouse gases just leveled off, they stopped increasing. Even with the extra amount we've already put into the air, some warming is still going to happen. So we've already locked ourselves into a little bit more warming. So the real object here is to reduce the amount of these greenhouse gases that we're putting into the atmosphere. That's as a population. That's the most effective measure. It's the most reliable scientifically. That's safer than trying to play around with any engineering solutions like changing the surface of the ice cover.
Do you think if the animals would extinct or move away?
That's a concern that the scientists have raised in this latest climate report. In looking at the world as a whole, they've estimated that maybe 10 or 15% of the animal species are at risk. So there is that possibility. If climate changes by those amounts that we saw in that little animation where it got red and hot, we could actually lose some species of animals. And in higher latitudes like Alaska and northern Canada, ecosystems that contain these animals are more sensitive. They have less diversity, so they're a little bit more vulnerable to climate change. So I think we do have to be concerned, and this attention that's being given to the polar bears is one example of how people are singling out what might happen if climate continues to change the way it is. Now this one's from Teller. It says, will global climate change bring about evolutionary changes in the human species? That's an interesting question. Over the long term, it might. And by long term, we mean thousands of years. But I think what's likely to happen much more rapidly is that people will migrate to different areas. Some areas will become too hot for living and too hot for agriculture, for the industries that keep people living in certain areas. And as climate changes and the agricultural zones and the temperate climates move north, people are going to have a tendency to migrate northwards. So I think that will be the, and that could happen over the time scale of several decades or a century, whereas the evolutionary changes would probably take thousands of years. So I think the more immediate thing we'll see is that certain areas will experience in-migrations. People will move there just because they become climatically more desirable as places to live. Second question from Teller is an interesting one. It says, what countries are doing something about carbon dioxide and climate change? Turns out the European countries are probably farthest ahead on this, and one good example is Norway. Norway has an interesting tax system. If you were to buy a car in Norway, cars emit a lot of the carbon dioxide and methane that goes into the atmosphere. If you were to buy a car in Norway, they charge a tax of 100%, which means you have to pay double the price of the car in order to buy a car. And they passed that law to discourage people from buying cars and doing extra driving. Some of the other European countries have taxes on gas. The cost of a gallon of gas is about double in Europe what it is in most of the United States, because the European countries are taxing gasoline. And several countries have, in fact most countries, have adopted what's called the Kyoto Protocol, which is an agreement to reduce greenhouse gas emissions by about 2020. So the United States and Australia and a few other countries have not signed that agreement yet. But the fact that most other countries have points to this difference among countries. So when we say that by contacting legislators and senators, we can perhaps get the U.S. to catch up with some of the other countries, I think we have one avenue to make things a little bit more equal in terms of how countries are responding to climate change. And then the last question from Teller, will listing the polar bears as endangered force governments to reduce greenhouse gas emissions, or will it just impinge upon the individual uses of the resource, polar bears? That's an interesting question, because there are going to be some impacts in Alaska. There will be impacts on individual uses. Essentially, anyone who wants to hunt or do something in a polar bear area will have to show how they're not going to adversely impact the polar bear population. And the example that people cite is what the oil and gas industry will have to go through. In northern Alaska, the oil and gas drilling is big business. In fact, it brings the state most of its revenue. Alaska's revenue really is dependent on the oil and gas activity up near the North Slope. The permission process that oil drillers and oil producers will have to go through will get very complicated. So there's concern that If this polar bear endangered species resolution is passed and becomes law, there are going to be consequences for industry. One could make the case that if the oil industry is impacted, maybe that will help to reduce greenhouse gases because there would be less oil produced, at least in Alaska. But it's a very complicated issue, and it will affect people at the individual levels and at the state and the national levels. So I think the final word has not been written yet on this Polar Bear Act, but it does have several sides of the coin. Okay, we have a couple from Shishmaref here. First one, is there a reason why the ice mainly leaves north of Alaska and not over Canada and Greenland? That's a good question, and there is a reason. The ice over Greenland is, in fact over Canada too, is thicker than the ice over Alaska. So it's much easier to melt the ice near Alaska in one spring or summer than it is over Greenland and Canada. The ice on Greenland is an ice sheet. It's a great big buildup of ice on land, and that ice is about a mile or even 2 miles thick in the middle. So that's not going to go away from just a summer or even a decade of warmer weather. The ice that's up over Canada is thicker than the ice west and north of Alaska. The ice offshore of Canada is something like 10 or 15 feet thick, whereas offshore of Alaska, even at the end of winter, the ice is maybe 4 feet, 6 feet thick. So it's much easier to melt away the ice in spring and summer when sunlight gets stronger near Alaska, just because it's thinner. So I think the thickness is the key factor there. And the other question from Shishmaref is, when will the permafrost be discontinuous throughout the Seward Peninsula? That's a timely question that the scientists are looking into with their models. And there are areas where the permafrost is already degrading on the Seward Peninsula. The best estimates from the models that I've seen suggest a time frame of several decades to maybe the end of the century before we really have discontinuous permafrost all around the Seward Peninsula. So it's not going to happen in a couple of years, but the time frame is a few decades. That means within the lifetimes of many of us, it could actually become more and more discontinuous. If the growing season increases, will it help remove greenhouse gases from the atmosphere? That's an excellent question in terms of the carbon cycle and what photosynthesis does. If you've had, say, plant biology, you know that photosynthesis, which plants perform, actually absorbs carbon dioxide. So it takes up a greenhouse gas and stores it in the plants. The problem there is that plants also respire, they breathe, and that releases carbon dioxide, and then they also decay over time. After they've gone through their life cycle, they decay, and that decay process releases the carbon dioxide back into the atmosphere. So you could say that at least during a summer season, a longer growing season will bring carbon dioxide down a little bit, but in the long run, that carbon dioxide will get back into the atmosphere. In fact, when we looked at that carbon dioxide graph a while back, there were little ups and downs each year on that cycle. And that the ups and downs there represent plants taking up carbon dioxide in the summer, but then giving it back again in the wintertime. So in the end, the longer growing season will probably leave us with as much carbon dioxide in the air as we had with a shorter season. Question from Teller: what would happen to the world when the world's really warm? Well, there are going to have to be some major changes, and I think this brings us back to the migration patterns. There are going to be some areas that are not livable, either because they become too hot or because they become too dry. If that drying that we talked about for Alaska becomes worse in areas such as the central U.S., where they grow a lot of wheat, people are not going to be able to carry on agriculture, and they'll be forced to move away. So there will be migrations. Now, the hope is that some areas will become more suitable for agriculture. Canada, Russia, and Alaska are possibilities. So when the world is really warm, those areas are going to have to provide the missing agriculture that other areas have been forced to give up. So as the world becomes really warm, that migration of people and agriculture and even water availability will move farther and farther north. So in a sense, we have an advantage there in that we are farther north. We're probably not an area where people are going to be forced to move away from because it's too hot or too dry, but there's still the adverse impacts, and we saw some examples of that in the slides we went through. Is there an upside to global warming? There are. In fact, the country that keeps pointing out these upsides is Russia. I think Alaska can be pointing to some examples too. But one of them has to do with the fact that with global warming, the winters are warmer. Now that's not good in some respects, but it is good in other respects. If winters are warmer, it means that the amount of heating we have to do to stay warm in our houses and in our other buildings is not as great. So we actually need less energy for winter heating as global warming sets in. And in that respect, it's perhaps we're perhaps lucky that the warming is largest in the winter and smallest in the summer. If the warming was largest in summer, we'd have to start worrying about getting air conditioning more than we do. But at least in winter, we can reduce the heating costs. The other upside is that this longer growing season for the high latitude areas means there are more opportunities for agriculture, more opportunities for forestry. So that's a plus. And the fact that the ice is receding is unfortunate in some respects. It's a bad thing for polar bears and then for some other types of marine mammals, but it does make the Arctic area, the Arctic seas, more accessible. And in Alaska's case, there's thought to be a good bit of oil and gas deposited below the sea surface, just offshore. The accessibility of those resources will improve. The irony there is that oil and natural gas are they're greenhouse contributors. So we're actually making the greenhouse producers more accessible by opening up the ice pack north of and west of Alaska. A question from Shishmaref. Some have said that Al Gore's An Inconvenient Truth has a lot of bad science. What portion is characterized as bad? That's an excellent question. Most of the scientists I've talked with have pointed out there is some bad science in that movie, although there's also a lot of good science in there. And I think most scientists feel that the good science outweighs the bad science in the movie. But as an example of the bad science, one thing that's been criticized is the way that movie held up Hurricane Katrina as an example of something global warming and the greenhouse effect is doing. There's a lot of debate about whether hurricanes and tropical storms will really be affected by greenhouse warming. And in general, holding up one single event as a sign of greenhouse warming, that means one single storm or one single flood or one single drought, gets to be rather risky because bad storms and bad floods and droughts would happen anyway, even without greenhouse warming. They just might happen less often without the greenhouse warming. One other area of bad science had to do with the sea level rise that they showed in the movie. That sea level rise was based on Greenland melting. And we talked about this a minute ago. Greenland does have enough ice that could raise sea level by 20 feet if all that ice became liquid water and reached the ocean. But that would most likely take hundreds or thousands of years. And the movie sort of implied that could happen much sooner. So I think some people were a little uncomfortable with that one. But again, on balance, the movie's message was, in the views of most scientists, a good message, and the science was not all that bad. It could have been a lot worse. Question from Teller. Compare the science in the
I think this is movies.
in the movies to real science. Okay, this is a good follow-on to the last question. I think Al Gore is an example of a politician who has actually talked with a lot of scientists, what we call the real scientists in your question. He's actually held meetings where he's called real scientists in. So in his particular movie, I think the science got a fair treatment for the most part. Again, we could find those details that we could call bad science. But a movie that I would call not so good science is that one about the day after tomorrow, where they showed the world, the ocean currents shutting down and the world suddenly getting colder by about 50 degrees in 5 or 10 seconds as the effect of that swept through the cities. And New York City was suddenly buried under snow that was as high as the Empire State Building. And that happened essentially in one big storm. That's an example of not so good science. So I think the answer to the question here is that we can find examples that go both ways. There's been some good science in the movies lately and some not so good science.
Could global warming result in the extinction of humans? And if humans became extinct, would the Earth then recover from global warming? That's interesting.
Well, that's a big picture question.
Yeah.
I think as far as extinction goes, it's a real long shot, but we have to look at the overall situation. With global warming, people will probably not die out because of the heat itself. But what global warming can do is create shortages of water, for example. Water is one of the big concerns. It's a concern already, and it could become a more serious concern if the world becomes warmer and drier. If there are water shortages, then there are going to be political tensions, and that could raise the likelihood of wars or other types of conflicts, and that could actually lead to some large-scale casualties on a scale faster and perhaps more widespread than the higher temperatures by themselves would. Then if humans became extinct, would the Earth then recover from global warming? That has some interesting implications here. If humans were extinct, we would certainly cut down on the fossil fuel burning. I mean, there'd be occasional forest fires, but we would not be burning oil, natural gas, and coal. So the greenhouse gas concentrations would stabilize, and over the long term, meaning hundreds or maybe close to thousands of years, there probably would be a return to equilibrium levels of carbon dioxide. So the irony there is that after hundreds or 1,000 years, we'd probably come back to the carbon dioxide levels of the pre-industrial times. So the Earth, or the atmosphere in a sense, would recover. Now whether humans would recover once they're extinct, I think is harder to say, but I think the case could be made that the recovery would occur in the absence of humans. It would just take a long time, hundreds to 1,000 years, because the carbon dioxide that's in the atmosphere takes hundreds of years to work its way out. That's an interesting question. I'd like to thank everyone for joining in, and I think, like we said at the start, you're at what many people consider ground zero. So your questions show that there's some thinking going on out there that's consistent with these changes we're seeing.